Welcome all to the course of Data Communication Networking, B7 semester, Electronics and Communication Engineering. We are discussing a local area network, unit 5, in which a last point in the unit is virtual circuit networks, just like our frame relay and ATM. So in the previous chapters, we discussing switching techniques. We said that there are three types of switching: circuit switching, packet switching, and message switching. We also mentioned that packet switching can use two approaches: a virtual circuit approach and a datagram approach. In this point, we show how our virtual circuit approach can be used in a wide area networks. Two common wireless LAN or VLAN technology use a virtual circuit switching. Frame relay is a relatively high speed protocol that can provide some service not available in other wireless LAN or WAN technologies such as our DSL, cable TV and T lines. ATM as a high speed protocol can be super highly of a communication when it deploys physical layer carriers such as our SONET. We first discuss our frame relay over here, then we discuss an ATM a greater detail. Finally, we saw how our ATM technology, which was originally designed as an VAN technology, can also be used for a LAN technology just like our ATM LANs. Fine. So we start with our frame relay. So frame relay is a virtual circuit wide area network that was designed in a response to demands for a new type of a wireless area network or wide area network in 1980s and early 1990s. So following topic to be discussed in this section: architecture of our frame relay layers, extended address, FRADs, VOFR and LMI. So prior to frame relay, some organization were using a virtual circuit switching called as an X.25 that performed switching at our network layer. For example, the internet, which needs a wide area network to carry its packets from one place to another, uses a X.25. Fine. And our X.25 is still being used by the internet, but it's being replaced by our VANs. However, our X.25 has several drawbacks. Just mention over here that X.25 has a low 64 kbps data rate. By 1990s, there was a need for a higher data rate of WANs. Fine. So there is a low data rate over here. Second, X.25 has an extensive flow and error control at both data link layer and the network layer. This was so because our X.25 was designed in 1970s when an available transmission media were more prone to errors. Flow and error control at the both layer can create a large overload and slow down the transmission. X.25 requires acknowledgement for both data link layer frames and network layer packets that are sent between nodes and between source and destination. Third, originally X.25 was designed for a private use, not for the internet. X.25 has its own network layer. This means that the user's data are encapsulated in the network layer packets of X.25. The internet, however, has its own network layer, which means if internet wants to use X.25, the internet must deliver its network layer packet called as an datagram to the X.25 for encapsulation in X.25 packet. This doubles the overhead. Fine. A disappointment with X.25, some organizations started their own private WAN by leasing T1 or T3 lines from public service providers. This approach also have some drawbacks. So what are the drawbacks for T1 or T3? If an organization has n branches spread over an area, it needs n into n minus 1 by 2 T1 or T3 lines. The organization pays for all these lines, although it may use the lines only 10% of the time. It can be very costly. The service provided by T1 and T3 lines assume that the user has fixed data rate for all the time. For example, a T1 line is designed for a user who wants to use the line at the constant 1.544 Mbps. This type of service is not suitable for many users today that need to send a bursty data. For example, a user may want to send a data at 6 Mbps for a 2 second, 0 Mbps for a 7 second, or 3.44 Mbps for a 1 second. So total 15.44 Mbps during the period of 10 seconds. Although the average data rate is still 1.544 Mbps, the T line cannot accept this type of demand because it is designed for a fixed data rate, not the bursty data rate. The bursty data require what is called as a bandwidth on demand. The user needs a different bandwidth allocation at a different time. In response for our mentioned drawbacks, frame relay was designed. The frame relay is a wide area network with the following features. A frame relay operates at a higher speed, just like our 1.544 Mbps and recently 44.376 Mbps. This means that it can easily be used instead of a mesh of T1 or T3 lines. Second, our frame relay operates in just the physical and the data link layer only. This means it can easily be used as a backbone network to provide a service to protocols that already have a network layer protocol such as internet. Third, frame relay allows a bursty data. Fourth, frame relay allows a frame size of 9000 bytes, which can accommodate all local area networks frame size. Fifth, our frame relay is less expensive than other traditional WANs. Last, our frame relay has an error detection at the data link layer only. There is no flow control or error control. Only detection is there. There is not even a retransmission policy if our frame is damaged. It is silently dropped. Frame relay was designed in this way to provide fast transmission capability for more reliable media and for those protocols that have flow and error control at a higher layers. Fine. So there are various good feature for our frame relay. So let's go for a architecture. Our frame relay provides a permanent virtual circuit and switch circuit, as you can see. Our figure shows the example of frame relay network connected to the internet. Relay network is connected to the internet via this WAN. The routers are used to connect our LAN to WAN and WAN to internet. In this figure, frame relay WAN is used as a one link for a global internet. So virtual circuits. Our frame relay is a virtual circuit network. A virtual circuit is and a frame relay is identified by the number called as an data link connection identifier, DLCI, data link connection identifier. So we can say that in the VCIs in the frame relay are called as an DLCIs, virtual circuit identifier. Fine. So what is the difference between permanent and virtual switched virtual circuit? So a source and a destination may choose to have a permanent virtual circuit called as an PVC. In this case, the connection setup is simple. The corresponding table entry is recorded for all switches by the administrator remotely or electronically. At outgoing DLCI is given to the source and incoming DLCI is given to the destination. PVC connections have two drawbacks. First, they are costly because the two parties pay for the connection all the time, even when it is not in use. So PVC connection have two drawbacks. First, they are costly because the two parties pay for the connection all the time, even when it is not in a use. Second, a connection is created from one source to the one single destination. If a source needs a connection with a several destination, it needs a PVC for each connection. So an alternate approach for is called as an switched virtual circuit, called as an SVC. The SVC creates a temporary short connection that exists only when the data are being transferred between source and destination. An SVC requires establishing and terminating phases, as we have discussed in the previous section. Next is switches. Each switch in a frame relay network has a table to route frames. The table matches an incoming port DLCI combination with an outgoing port DLCI combination, as we have described for the general virtual circuit networks. The only difference is that VCIs are replaced by the DLCIs. Okay. So next is frame relay layers. Our figure shows the frame relay layers. Frame relay layer has only physical and the data link layer, as you can see over here. Frame relay operates only the physical and the data link layer. At a physical layer, no specific protocol is defined for the physical layer in a frame relay. Instead, it is left to the implementer to use whatever is available. Frame relay supports any of the protocols recognized by ANSI standards or ANSI standards. Data link layer. At a data link layer, frame relay uses a simple protocol that does not support flow or error control. It only has an error detection mechanism. Our figure shows the frame format over frame relay frame. The address field defines a DLCI as well as some bit used for a control congestion. Following fields can be discussed over here. First is address field or DLCI field. A first 6 bits of our first byte make up a first part of the DLCI. The second part of the DLCI uses a first 4 bits of the second byte. These bits are the part of the 10-bit data link connection identifier defined by the standards over here. We will discuss extended addressing at the end of this section. CR or command and response. The command response bit is provided to allow upper layers to identify a frame as either a command or a response. It is not used by our frame relay protocol. EA or extended address. Extended address bit indicates whether our current byte is a final byte of the address. An EA of 0 means that another address byte is to follow. An EA of a 1 means that the current byte is the final byte 1. Next is FECN, called as an forward explicit congestion notification. The forward explicit congestion notification bit can be set by any switch to indicate that the traffic is congested. This bit informs the destination that congestion has occurred. In this way, the destination knows that it should accept the delay or a loss of packets. We will discuss the use of this bit when we discuss the congestion control in a future chapter. Next is BECN, means a backward explicit congestion notification. The backward explicit congestion notification bit is set in the frames that travel in another direction to indicate a congestion problem in the network. This bit informs the sender that the congestion has occurred. In this way, the source knows it needs to slow down to prevent the losses of packets. We will discuss the use of bit when we discuss the congestion control in a future chapter. Next is DE, means discard eligibility. The discard eligibility bit indicates the priority level of the frame. In emergency situation, switches may have to discard frames to relieve bottlenecks and keep the network from collapsing due to the overload. When set D is equal to 1, this bit tells the network to discard this frame if there is a congestion. This bit can be set either by a sender of the frames or by the any switch in the network. So, we can say that our frame relay does not provide the flow or error control. They must be provided by the upper layer protocols. Finally, EA. EA means extended addresses. To increase the range of an DLCI's frame relay address has been extended from the original 2-byte address to the 3 to 4-byte address. Fine. This figure shows the different addresses. Note that our EA field defines the number of bytes. It is a 1 over here in the last byte of an address. It is a 0 in the other bytes. Fine. Note that in a 3 to 4 byte formulas, the bit before the last bit is set to 0. Fine. Over here, the last bit is 1, then upper byte or previous byte will be zeros. Over here, a 4-byte address, a 4th byte EA is equal to 1, then our previous ones have a 0 value. Next is FRDA. FRDA means a frame relay assembler deassembler. To handle the frames arriving from the other protocols, frame relay uses a device called as an FRDA or FRAD. An FRAD assembles and deassembles frames coming from other protocols to allow them to be carried by the frame relay frames. An FRADs can be implemented as a separate device or a part of a switch. Our figure shows the two FRADs connected to the frame relay network. Fine. Over here, FRAD 1 and FRAD 2. A frame relay network over here. VOFR, a frame relay network, offers an option called as an voice over frame relay, called as an VOFR, that sends or send a voice through the network. Voice is digitalized using a PCM and then compressed. The result is sent as a data frames over the network. This feature allows the inexpensive sending of the voice over the long distances. However, note that the quality of the voice is not as good as the voice over the circuit switch network, such as our telephone network. Also, the varying delay mentioned earlier sometimes corrupts the real-time voice. Second is LMI. LMI means a local management information. A frame relay was originally designed to provide a PVC connection. There was not therefore a provision for controlling or managing the interfaces. Local management information is a protocol added recently to the frame relay protocol to provide more management features. In particular, LMI can provide a keep alive mechanism to check if the data are flowing, a multicast mechanism to allow a local end system to send frames to more than one remote end system, a mechanism to allow an end system to check the status of the switch if a switch is congested or not. And finally, a congestion control and a quality of service. One of the nice feature of our frame relay is that it provides a congestion control and a quality of services. We have not discussed this feature yet. In future chapter, we introduce these two important aspects of the networking and discuss how they are implemented in a frame relay and some other networks. Fine. Okay, so it is a end of our session. Let's revise our discussion. In the first, we have defined a virtual circuit networks in which a frame relay and ATMs are covered. Then we introduce a frame relay. We also discuss the drawbacks of X.25. Then a feature of frame relays. Then architecture of a frame relay. We define a data link connection identifier. Then we introduce a PVC and SVCs and switches. A frame relay have a 2 layers, physical and data link only. Then a frame structure or a frame format of our frame relay. After that, an FRAD and VOFR and LMI is discussed in this section. So it is a question for you. Write down in your notebook and send back it to me as per the given direction. Okay students, see you in the next session. Thank you.